Hello and welcome to the warehouse design presentation for the WRAM 2 data warehouse project. This presentation is aimed at all levels of technical understanding, although it is recommended that you know about the WRAM wireless remote animal monitoring project before you view it. This has been put together for the customer workshop on March 13th, 2013 and provides an overview of what design decisions have been made, as well as giving an insight into the reasons why. It should be noted that some of the diagrams have been simplified to provide a conceptual description rather than a full and complete technical description of the subject matter. This has been done to ensure that the presentation does not become bogged down in too many technical details. So, we will choose to start at the beginning as we did 18 months ago with a question. What design considerations and requirements do we have for the new data warehouse? First is constant 24/7 updates. From GPS sensors to temperature, heart rate and activity sensors, whilst the wearer might sleep, the sensors do not. So WRAM receives a constant stream of data from the field. But why is this so important? Well, as with cakes, you can't keep a slice and eat it. With databases in general, you cannot load data whilst maintaining the same end-user query performance you want. The more data you load, the higher the impact on the end user. And let's be honest, there are few end users out there who don't want their data in its entirety now. We're all used to web pages being cached in Google Chrome before we click on a link. In addition to wanting their queries to be available promptly, users want the data that is returned from the field to be loaded and available quickly. It's no use chasing after an animal in a helicopter if the data on your tablet is over 30 minutes old. Our next requirement is to have a warehouse that has similar performance 24/7. As WRAM has developed, so have the geographical spread of its users and the time of day in which they are most used. So 24/7 365 is very important. In addition, we should also consider the ever greater range of users. These user groups, such as members of the public, wildlife managers and researchers, have certain generalized patterns of access. Public users tend to want to know where animals are near their home or summer cabin. Wildlife managers want to track their animals today or recently, and researchers, well, they don't want to be pigeonholed, but it's enough to say that they want anything historic data or new, local, regional or national. Our next requirement is to consider the ever-increasing diversity of sensors and the data that they send back. New sensor types have been developed and deployed. GPS may have been the mainstay of WRAM 1, but today we have added sensor packages on the collars such as activity. We have sensors being swallowed by animals and relaying data to the collar, reporting on body temperature and heart rate, and camera size and energy use are being shrunk to the point where these are also going to be included. As well as new sensors, we have new and changeable data formats. As manufacturers develop their sensor products, so their software and choice of data format can develop as well. To add to this, we have new communication methods being used. The original days of GSM-based SMS messages is being replaced with the possibility of direct data transfer or push, expanding the amount of data that can be sent and the technology used. This will come as no surprise given the previous slide. As WRAM devours ever more sensor data from more animals, the design must be able to cope with the increased data storage. As sensor packages are developed, becoming smaller and cheaper, it is likely we will gather increasing amounts of data from individual animals and from larger groups. Currently, we may have 2 sensors on a tag or a collar, but in future this could grow considerably. As well as more animals and sensors being deployed, the data we're collecting, as mentioned before, is simply becoming bigger. A GPS position might have taken up 1 kilobyte of storage in the past, but now if a photo is being taken from a collar-mounted camera, that might be 500 kilobytes. As with everything technology-based, we face the same challenge that as time passes, we must preserve or improve the system performance people expect as the amount of data increases significantly. So here is an overview of the considerations and requirements. The requirements are to minimize delay in loading data, to minimize the impact of this loading, support all new sensor data types, and designed for future growth. To help overcome some of these challenges, we decided to split the warehouse. We have two sets of data: old data that has been received, processed, and in general does not change; new data that is coming in quickly and needs to be processed and made available as soon as possible. So why not have two data warehouses? One where we put all the new data. It can be extremely small and very high performance. The delays caused to process and make available the new data will be very small. Then we can have a second warehouse that holds all the old data. Every so often we take older data from the first warehouse and move it into the second. So here is the conceptual design. It should provide extremely fast loading of new data. The end user will see only the single WRAM data warehouse. They won't see two separate warehouses. Similar or better end user query performance should be available than from a single warehouse design. So let's next look at the technical description. Here is an actual representation of how the system is designed. We have a staging area where all new data is received and processed. This is to ensure the data can be made available in a consistent manner. After this, the data is inserted in one of two duplicate data warehouses. The real-time data warehouse is very small and high performance. The historic data warehouse holds all the other data. The ETL process is split in two as well. The first runs every 3 to 5 minutes, loading new data and transferring it in to either the real-time or historic warehouses. 99% of new data will go into the real-time. Then a second ETL process runs daily during low system use, migrating the oldest data in the real-time warehouse into the historic. The benefits are as written: very fast loading and time to load, and this does not affect end-user query performance. SQL Server presents the user a single data warehouse, but only sends the query to the appropriate warehouse or both. The next issue we will look at is that the data we're storing from the sensors is different. One sensor might send back GPS-related fields such as longitude, latitude in a numeric format, whilst a camera returns either a large binary object or an HTTP link to the image stored on a server somewhere. If everything sent back an integer value, life would be very simple, but perhaps the data would not. As with WRAM 1, we could store all these different data table structures in different tables. However, this means system changes every time a change to the data format or columns takes place, or when a user's sensor comes online. These changes are quite significant. So one solution to this is to use NoSQL. NoSQL allows us to store in a single table different columns for different rows. A second solution is to use a generic table structure. A process of serialization takes a normal table, think of this as a parallel object like your old PATA hard disk in a computer with a very thick wide cable. This has many columns of data relating to one row, and we pull out the column values and insert them into a single table with a reference as to which column each value came from. Over the page we'll look at an example. In this example we have two sensors, a GPS sensor and an activity sensor. Each returns its data in its own format. Keep in mind that each manufacturer of sensor and possibly model could have its own unique format and require a unique table in WRAM 1. To serialize the data, we turn the columns into rows, similar to the pivot function in Excel. We store the values individually with a reference as to the type of value. This allows us to model almost any data in just a single table. A note here is that the value in the serial measurement table is numeric, and as such we need to convert dates and text into numeric values. This is not particularly useful, so we will end up with 3 serial measurement tables. One for numeric values, one for dates, and one for strings. Another benefit of this approach is that it is much easier to compare the battery life across all sensor types and similar types of queries. In round 1, we would have to link together a large number of tables and possibly convert values between them into a similar format. Two of our goals are to reduce manual administration with the warehouse and to increase the quality of the data. To these ends, we have built a quality control and correction system into the warehouse. This QC&C system takes data rules written by us that can either be used to measure the quality of a data record or correct a common error. An example of these is that the GPS points should not change radically. We can view where the previous position was and the maximum movement speed of the animal over time to gauge if a new position is appropriate. Also, we can correct common issues like the year coming through incorrectly. But why build the system? Well, this is so that we can give end users a view on the level of trust that they should give to different data sets and values, and to remove common administrative tasks. So the next thing we're going to do is to add value with metadata. Descriptive metadata, to be specific, data about the data content. So what do we mean by this? Well, metadata can be thought of normally as data about data, and in our particular example you can imagine that we will record data about the accuracy of the different GPS sensors, the make, the model, and which data quality rules have been applied in the results of these for each data value. The reason that we do this is again to enhance how research can judge a set of data or data points. Is a set of GPS data where the GPS receiver is brand new and has an accuracy of 1 meter, is that better for his or her research than 20-year-old data from a GPS receiver with a 5-kilometer resolution? Now clearly both of these data sets may be used, but the appropriate level of understanding is increased if we have this metadata. And that's planned for delivery Q4 2013. Data aggregation is a key requirement for the warehouse. This process allows us to present data through the data broker to LifeWatch and GBIF if the data owner wishes. It also allows end users to view combined raw data. It is easy to imagine and plot GPS positions of an animal or species. However, once you start having thousands of positions on screen, it becomes hard to track what the actual path was. Therefore, we can aggregate these points into a generalized movement track or line. Movement lines of an individual animal can be combined to give us a home range object, a shape that describes where the animal roams over time. Movement positions of animals, can be combined for some sort of group dynamics analysis. We could take the same data and aggregate it over a much larger timescale to gain a picture of migratory patterns. Whilst the WRAM data warehouse will offer a number of pre-aggregated data sets, we can't do everything, but we will endeavour to make it easy for users to do more themselves. This is planned for the following 6 months of development. Different data presentations will be provided. To ensure users are able to switch over to WRAM 2 easily, all of the standard WRAM 1 views will be preserved with minimal or no changes. This is already delivered and available. New views using the new features of WRAM 2 will also be made available. This is an ongoing development, more details of which will be finalised near the end of the project. However, as previously mentioned, the ability to query across sensor types will certainly be included. As part of these new views, it is hoped to deliver the WRAM 2 data in a multi-dimensional cube-based analysis system. Multi-dimensional analysis allows end users to quickly analyse across multiple categories or dimensions. A dimension can be imagined as species or time. It can also allow end users to use other data analysis tools. Our aspirational delivery of this is by the end of the project. Finally, the security of the system has been improved. The current WRAM 1 system uses slu's Active Directory. Whilst in many cases this can provide robust and appropriate authentication and data access, for the required levels of data access in WRAM 2, it is simply unable to cope without a significant amount of administration and performance overhead. A new security system built around standard industry practices with specific project enhancements has been implemented. This provides full row-level security, delivering data owners can easily grant access to their data to an individual or group. Data access can be removed or altered and applied immediately. Almost any field with the system can also be used to provide access. In addition to this complete RLS implementation, the system also provides partial cell-level security, CLS. For the actual sensor data, therefore, this allows access to be given on individual fields of data to an individual or group. Example is that we can now set user X so they can view GPS but not heart rate for animal A, B and C between dates T and S very easily.